Okay, everybody, so let's talk about springs, forces of compression and tension, and also Hooke's law. Now, I hope that you looked at the last video I made where I talked about if a force moves something, then the force does work and so on. And the main idea behind the video was how to develop a way to calculate the work done by a force that's not constant. And I gave you this model and I tried to make a big deal about it, that the model is that a force pushes something along the x-axis from one point to another, and that force is variable. It gets stronger or weaker as you push across the x-axis. And part of the objective was to come up with a formula for that force, like that at any point on the x-axis, f of x calculates how strong the force is pushing or pulling or whatever it is at that point, okay? That may have been the hardest part about the problems, was to figure that out. Now, springs fit into that all on their own, and they need their own video. So here's a video that you can do by the same thought process as the last one, but it will just focus on springs, okay? All right, so let's say that you've got a spring, and I had to tell you it's a spring because it's such a lousy picture, but say there's a spring and it will have a certain natural length. So nobody touches the spring and it's got a certain length to it, okay? You could stretch or compress the spring. If you stretch it, you're putting it in tension. If you compress it, you're putting it under compression. So say you take a spring that has a certain natural length to it and you want to stretch it or compress it. Then there's something called Hooke's law that governs the force required to hold the spring stretched or compressed a distance of x beyond the natural length. And it's F is equal to K times X. It just says the force required to stretch or compress a spring beyond the natural length is proportional to how much you want to stretch it or compress it. Now, you probably held a spring before, and like if you compress it, it resists being compressed. But the more you compress it, the more it resists being compressed any further. Same thing with stretching it. If you take a spring and it's a natural length of whatever, and you start pulling it, at first it doesn't resist being pulled so much, but the more you pull it, the more it resists being pulled any further. So the force required to hold it compressed or hold it stretched is proportional to how far beyond the natural length you want to stretch it or compress it, all right? So now you'll get that constant of proportionality, K there, and that will be unique to each spring, all right? So maybe like every spring could have the value of K stamped onto it, and then you'd have a working equation, all right? Now, so let's do an example based on this much, all right? So suppose a spring has a natural length of 0.2 meters, and a force of 2 newtons. Now, a newton is just a way you can measure a force. I gave you the conversion in the last video. I think a newton is about 0.25 or 0.22 or something pounds. It's just a way you can measure how strong a push or a pull is. That's what a force is a push or a pull. Make something move, okay? So a force of 2 newtons is required to hold it stretched to 0.75 meters. So it's 2 meters naturally, and then you hold it right out here with all this effort to a stretched distance of 0.75 meters. Calculate the constant K. All right. Well, all right. So we've got our equation. It says F was the force. X was the distance we were going to hold the spring stretched or compressed beyond the natural length, okay? So the force was given to be 2 newtons, and if I was going to stretch it from its natural length of 0.2 meters to a stretched length of 0.75 meters, then 0.55 meters would be how far I'm stretching it beyond its natural length. So that's the number that goes in there, all right? So I get my equation like so, and I can solve for K. So it's 40 over 11. 2 over 0.55 is 40 over 11. So here's what I have. For this particular spring, the force required to hold it stretched or compressed is 40 over 11 times x, where x is how far beyond the natural length you're going to stretch it or compress it. That's a working equation for that particular spring as described here. Okay? All right, now let's take it a little bit further. So think about this problem. A force of 7 pounds can compress a spring from its natural length of 15 inches to a compressed length of 10 inches. Okay, it takes 7 pounds to, like, the spring's 15, and if I want to squish it down to 10 and hold it right there, it takes 7 pounds of sustained force to hold it like that. That's what I'm saying. Okay? All right, so say I tell you that much. What force is required to compress the spring 9 inches beyond its natural length? So with this first data point right here, 7 pounds will hold it compressed to 10 from 15. Then what force is required to compress the spring down to 6, right? If I'm compressing it 9 inches beyond its natural length, and it's naturally 15, well, that would be like squishing it from 15 down to 6, all right? Okay, so here's how we'll go about answering it. We've got our working equation, okay? My first data point, the force of 7 pounds will hold it compressed. Why did I put 5 right there? Why didn't I put 10? What's x supposed to be? X is the distance beyond the natural length that sustained force can hold it stretched or compressed. That's 5. If it's 15 and I compress it down to 10, I compressed it 5 inches beyond its natural length. Okay, so there's my working equation, my first data point with my force and my x, and so k is equal to 7/5. I get this working equation now. See that equation right there? F, that's the required force to hold the spring, compressed or stretched a distance of x inches. Now we have to be consistent with our units. If we were measuring our distances in inches up there and pounds here, then those units are going to apply here. That's got to be x inches beyond the natural length. Okay? All right. So you got that working equation now. What force is required to compress the spring 9 inches beyond the natural length? Well, so I put 9 in this time. Okay? So you might be compressing it from 15 down to 6, but you know that number x is supposed to be how far you're stretching to compress it beyond the natural length. Well, it said 9, so I put 9 in. That's 12.6. It takes 12.6 pounds to squash that spring down from 15 inches its natural length to 6, okay? All right, so I got my answer. Now, I thought, let's do some comparisons in the strengths, okay? So the spring is naturally 15 inches. It takes 0 pounds to do that because that's its natural length. If you squash it down to 10, that takes 7 pounds. That's what I was told in this first data point. But then if you squash it down to 6, that takes 12.6 pounds of sustained effort to squash it down to 6 and hold it there, okay? All right. Now, isn't this like what I said originally? I said the more you displace this from its natural length, the more effort it takes, all right? Squashing it down from 15 to 6 is going to take a greater force than squashing it from 15 to 10, okay? All right, so 0 to 7 to 12.6 and beyond. Now, let's do something that follows from this. Say we're okay here. We understand our working equation for springs and how to interpret the force and the value of x and so on. Say we got that. Then here's the next thing that we do. Okay. Suppose we're dealing with the spring that I just talked about. Okay. Can you calculate the work required to compress it from a length of 15, which is its natural length, to a length of 6? Okay, so how much work? Now, I know that if I was going to squash it down from 15 to 6, and if I was going to hold it squashed down, like I'm putting all this effort, I'm squashing it down to that length, the force required to just hold it squashed like that is 12.6 pounds. Okay? That's the force of compression required to hold it to that 6-inch length. All right? But I want to know the work required to start at the natural length and gradually compress it to a final value of 6. All right, so there's my question. That's what I want you to think about. And here's how I think that we'll do it. I mean, what's my model? How do you calculate the work done by a force that's not constant? Would the force to compress the spring be constant? Well, no. I mean, the more you compress the spring, the more it resists being compressed. Okay? The more you compress the spring, the more effort it takes to continue compressing it. So if you were going to compress the spring from its natural length of 15, all right, and then push it down to where this end was at 9, it would gradually take more effort to do that. All right, so here's what I've done. I've taken my model where it says I want to move something from here to there, okay? And there will be some variable force that acts on whatever I'm pushing or moving, and that will be f of x, okay? So here's how I'll set it up then. In that context, I'll put the spring, and there's the x-axis. It's measured in inches. And suppose that like that end of the spring is fixed, and I'm going to push this end that way to compress it. Okay? So this end's going to start at 0. And I'm going to push it to where? 9. Why? Because if I push this end of the spring from 0 on the x-axis over to 9, I'll be compressing the spring to a length of 6. That's the difference between 9 and 15. So this end's going to be fixed. I'm going to push that end. Now, as I push this end, the force is going to get stronger as I go that way. It's going to take more effort as I continue to compress it. What's my equation? Is it this it? F of x is 7/5 x. Okay. So that was our equation when we worked with that same spring before, right? The nature of this spring is that the force required to compress it to various lengths is 7/5 times x. All right? So no matter where you are, you could say, what's the force required right there? Well, that number is how far beyond the natural length you've compressed it. That's why this does serve as my variable force equation as I compress the spring like this. Okay? All right, so I've got everything in the model. I'm going to take this, I'm going to push it that way. I'm going to push it from 0 to 9. The force required at every point along that journey will be this, okay? So all that goes in here. Push the end of the spring along the x-axis from 0 to 9, and that's the variable force required as I go along. Okay, that's a pretty easy integral to do, and you'll get 56.7. What are the units? So distance units, inches, and before when I gave my force units, they were in pounds, so that's going to be inch pounds. Okay, all right. So that's how we do our spring problems. It's no different. I mean, this will take some thought on your part, and I encourage you to understand the superficial parts of this, where you plug the numbers in and so on, but the deeper parts too. This is no different than that problem I mentioned of winding up a chain. We're just moving something along the x-axis in a straight line, however you position the x-axis, whatever, and the force that acts on this thing as it moves gets stronger or weaker as we go along, okay? So just think about that. Do you see why these would be proper bounds? Do you see why that really does tell me the force that's acting when the end of the spring is at point X? Like that this would measure the force required to be there. Okay, I want to make sure that you see all of that. Okay, so let's say if we're okay with that. All right, so we got that, we understand it, and we get to the point where we move on to the next thing. So I'll take a problem that's just, it goes from where we were with that last one and takes us a little bit further. Okay, so suppose I tell you that 2.5 foot-pounds will compress a spring 3 inches from its natural length. Okay, first data point, 2.5 foot-pounds of work will take the spring and start at the natural length and compress it, squash it down 3 inches. Okay, So what are these units here? These are work units. Am I saying 2.5 pounds is the force required to hold it compressed? Yeah, there's two different things there. There's the force required to hold the spring compressed and the work required to gradually compress it. Two different things, okay? The force required to hold it versus the work required to go through the process of compressing it, all right? So maybe I haven't emphasized that enough, but they're two different things, okay? A force is just a push or a pull, and work is when a force makes something move, okay? All right, so 2.5 foot-pounds of work will compress a spring 3 inches from its natural length. Calculate the work required to compress the spring from 3 inches to 3.5. So it's, you know, if I can work with this, does that give me enough information to figure that out? Okay. So first of all, I think we need to be consistent with units. All right. In math, we don't have to worry about units quite as much. If you ever take chemistry or physics or something like that, like a science that's based on measurement, then you really have to spend a lot of time thinking and learning about units. All right. Okay. So this is in foot-pounds. That seems to say that the distances were measured in feet and the forces were measured in pounds. And then over here, I'm given distances in inches, and I just need to be consistent. So how about this? We either need to use inches or feet. We can't mix them up. So I'm going to convert 2.5 foot-pounds to inch-pounds. All right. So 2.5 foot-pounds. All right, well, 1 foot is 12 inches, so I'll multiply by 12, and that will be 2.5 times 12, which is 30 inch-pounds. Okay? All right, now, it said here, oh, whoops, I'm sorry. Okay, so I put 30, for a minute I thought, oh no, I need to put the work there. So it's 30 inch-pounds. That's the work. Here's our work integral. Okay, 30 inch-pounds will compress a spring 3 inches from its natural length. So it's like 0 says we're starting, if you think about the last problem, at the natural length over to 3 inches beyond the natural length. We don't know K yet, but there's our governing force equation for the spring. But I know this integral will be 30 because that is the measurement for the work required. So work equals, there's my work integral, and I'll get 4.5 K out of this, all right? So, okay, 30 is 4.5 K is what this reduces to. You can solve for K, 30 over 4.5, that turns out to be 20 over 3. So now I know K, right? Knowing the work required to compress the spring 3 inches from its natural length, knowing that that is calculated from this integral, I solve for K. There's my working equation for the spring. The force required on the spring to hold it stretched or compressed, distance x beyond the natural length, is 20 over 3 times x. Okay. Now, that second part of the problem was to calculate the work required to compress the spring from 3 inches compressed. So it's like, got this natural length, and say I've got it compressed to 3, and then I want to compress it from 3 to 3.5. So how much work required to compress it that extra half of an inch? Okay, so I'm holding it at 3, and I want to compress it another half inch. How much work required to push that extra half inch? That's what it's asking us. So, okay, now we look at that other problem I showed you, here with this one. I showed you some detail about how I envision the spring on the x-axis and so on, and I talked about it like the problems in the other video I made. But what will happen is that will be the force equation. This is where we're going to start. Okay. And here we started with the spring at its natural length, and then I wanted to compress it to 6. Okay, that means 9 beyond natural length. Okay, so that's where we end. We started at the natural length, and I want to compress it 9 inches beyond the natural length. If it's naturally 15 and I compress it down to 6, that's 9 beyond. All right. So as a result, then here, to compress it from an already compressed 3 beyond the natural length, okay, an extra ½ inch, that'd be like from 3 to 3.5. All right, so I'm going to start at 3, already compressed, and I'm going to compress it down to 3.5. So that's the work required to push it that extra ½ inch. So I get my equation, my working formula for the spring 20/3 times x. I have my antiderivative, easy to do. I put my numbers in, I get 65/6 inch-pounds. Now, from here, I get 65/6 inch-pounds. That's the answer. Why inch-pounds? Well, because I was dealing in foot-pounds, meaning that forces were measured in feet, forces were measured in pounds and distances in feet. And just to be consistent with the units, I converted the distance measurements to inches, okay? So that's why that's in inch-pounds. And if those are the units that were required of you, then that's your answer. It might be just because we are using different units of measurements that they could ask you for foot-pounds, all right? Or any other measurement that we can convert to. So let's suppose that I give you this. Like, here's your answer. To compress it from 3 to 3.5, the work required to move it that distance is going to be 65/6 inch-pounds. Suppose I want foot-pounds. I just have to convert that inch measurement into feet. Okay, and the conversion is 1/12. Okay, 1/12 feet is an inch. 12 inches is a foot, you see? So there we go. That would be my number in foot-pounds. Multiplying those together, I'll get about 0.9 foot-pounds. Okay, I'll just consider both these correct because it would all depend on what units you're being asked to give. But what we learned in this problem is the nature of the integral for springs, okay, how to calculate the work done in pushing the spring, compressing it or stretching it, so on, and how we need to be consistent with our units. We can't mix up different units of measurements for the same thing. If you're going to use feet everywhere. If you're going to use inches everywhere. Okay? Now, if you seek help somewhere else or you get other opinions on this, somebody else could have converted these measurements to feet. All right? And just as long as you get agreement, that's all that matters. I converted the foot measurement here in my work calculation to inches, but I could have converted my inch measurements here to feet. They just have to agree. That's all we really have to worry about.